Okay, so shall we start? And good morning, everyone, and thanks for attending today's data science seminar. And a special thanks goes to Sharon for generously dedicating her time to share her research insights with us. And now I would like to take a moment to provide a brief introduction to Sharon. Sharon is currently an assistant professor at the University of Wisconsin-Madison, and she received a PhD from Cornell University and was a postdoc scholar at Stanford University. Her research focuses on algorithmic and theoretical foundations of learning in open world. Without any more delays, and over to you, Sharon.
Well, thank you so much, Yadan, for the invitation and for the kind introduction. It's a great pleasure for me to be here at the data science seminar. Today, I would like to share with you all about some interesting research challenges and progress we've made on this direction of out-of-distribution detection. This is a problem that's really close to my heart, and my lab has been working on this problem over the last couple of years. And so I would like to start the talk by showing you this video. If you're looking at this video, this is a perception model trained on the Berkeley Deep Drive 100K dataset, or called BDD dataset, performing bounding box tracking on the road. And whenever we see videos like this, it's really easy to be carried away by these seemingly powerful capabilities that modern neural networks have demonstrated. And in my research, my mission is to encourage researchers and practitioners to look at the other side as well, especially take a cautious view at these methods and technologies that we built, especially when it comes to unexpected situations that the model wasn't trained for. And so hopefully by the end of this talk, we can see things in a more well-rounded perspective. And so let me provide more context on what I mean by that. Perhaps, one activity I would like the audience here today to do is now, imagine you're wearing this hat, right? Being, leading an AI team at a self-driving car company. Whatever your favorite is, be Tesla or something else. My question is, how would you approach building and then deploying such a self-driving car model that can function reliably in the real world? So if we're going to abstract this process a little, we typically would start with gathering training data, where we would annotate these data points individually into some predefined categories. And then we would train on our favorite machine learning model, say a neural network. And here the output would typically contain some predefined categories. In this case, we're interested in detecting pedestrian, cars, and truck, and maybe traffic light, and so on. And so the model is kind of trained to minimize these recognition error. And so, of course, this is an oversimplification. In practice, every single step is going to require a lot of work to figuring out all the details. But let's say you've navigated through all these challenges, right? And finally, reach the point where the model has a pretty decent performance on this training task. And so once you deploy these models, roll this out into the real world, this is where a lot of trouble starts to happen. The reason I say that is I think it's widely acknowledged that training and test data distributions may not necessarily match each other, right? This is what's known as the open world scenario, which better captures the real world than the very idealistic assumption that we've often made, in our machine learning textbook, which is closed word scenario. And so in the open world, a lot of unknowns can emerge, and these unknowns can happen or occur in situations that the model just simply wasn't prepared for. To give a concrete example, in our iClear work, in collaboration with my PhD student Shufeng, we looked at the model just trained on the BDD dataset. Then we took this model and then evaluate on this image, this particular photo that I'm showing you in the slide right now. It's actually from a different data set called MS Coco. And keep in mind that this image was never part of the training, right? And so we take this image and run through the self-driving car model that was trained on BDD. And so interestingly, you can see that the model trained on BDD, which is our in-distribution data set, can produce overconfident predictions for this unknown object, which is helicopter right in the middle. And so in other words, deep neural networks do not necessarily know what they don't know, right? In reality, you don't want this helicopter to be blindly predicted into a truck, right? Because truck is, obviously one of the in-distribution categories, but the helicopter has nothing to do with any of those training categories. And so this has raised significant concerns on models' safety and reliability. As you can imagine, algorithms that just blindly classify such out-of-distribution samples into one of the known classes can be catastrophic. And ideally, we want the model to be able to flag automatically such scenario, and to be able to say something like, oh, this is something I don't know, so that human can take precautions and can intervene, right? So that's the ideal situation here. And believe it or not, this kind of situation can happen in real life and causing real consequences. So here I'm quoting a news article from April last year, which reported that a Tesla vehicle in the self-driving mode crashed into this private jet, which also happens to be in this blue color. And so I wish I could play this video, but I can describe what's happening. If you're interested, you can actually go search online about this original video. So what's happening is this white car is driving towards this blue jet right from far. And as soon as it hits this the blue jet, it starts kind of rotating and spinning around. Unfortunately, no one got hurt in this incident, but you can imagine, right, the gravity of this issue in some other safety critical scenarios. And so this research problem of out-of-distribution detection has become very, very important. And hopefully at this point, I've convinced you why it's an important and meaningful problem to work on. And so this is going to be the focus of my talk today. So what is out-of-distribution data? Let me first provide a simple view so that we can, contextualize this problem setting. Let's say we have our training data distribution. In this case, just for simplicity, consider a mixture of two Gaussians with two labels, y equals to 1 and y equals to -1. And our in distribution would be the marginal of the joint distribution over the input space. So basically what's this green the green contour highlighted, right? That's our in distribution Pn. And during test time, these orange dots could emerge, which are out of distribution from an unknown class that doesn't belong to either y equals to 1 or minus 1, and therefore should not be predicted by the model. So in other words, the particular type of out of distribution we're tackling here, we're focusing on here is more on the semantic shift side, right? And so any novel classes that could emerge during test time, that's something we want to catch. And to translate this toy data into some high dimensional images, you can think of cipher 10 on the left-hand side to be the in distribution, which may contain categories such as cats and dog, frog, horse, and so on. And on the right-hand side is just one example of out of distribution, say street view housing number. And clearly, these images on the right-hand side have, completely different semantics from the left-hand side. And therefore, you don't want to use a model trained on cipher 10 to make prediction on any samples on the right-hand side. Well, you might think this setup is too easy, right? At least too obvious to humanize, and I would agree with that statement. But surprisingly, when the field started many years ago, one of the first works on OOD detection, back then it was a very challenging task. If you're looking at this FPR, the error rate that the OOD detector is making on such a detection task, it was actually surprisingly hard many years ago. But of course, a lot of research progress has been made over time, and I'll share and touch upon some of those later in my talk as well. And of course, in reality, we need to consider much more sophisticated OOD detection scenario than this. So I'm also going to be talking about how we can go beyond such simplified definition. But let's start with this the simple view and build from here. So SVHN is just one of the OOD that the model would encounter. And there are, of course, many other unknowns on the data manifold. And so this is a slide I'm quoting from a talk given by a researcher at OpenAI. And I think it's quite a nice illustration in terms of the nuance and complexity of this problem. And so the right-hand side, as you can see, contains all the possible images that one could generate and encounter on the internet. And this is in sharp contrast to the left side, which is often a task-specific data set, right? So that's the ideal world we were used to be in, right? Assuming training a model on cipher 10 and encounter sample only from that distribution. And the right-hand side is where the reality is. And so out of distribution detection is actually a pretty challenging problem. And I want to use a few slides to explain the why before we get into the how, the solutions. So what are the challenges? The first challenge is that the model is typically trained on the in-distribution data, I would say in the most classic setting. So in this case, we may train a classification model using empirical risk minimization on the points belonging to the green and the blue classes, respectively, right? And so once the model is trained, you're going to be deploying this to be the real world. And the challenge here is you can't really anticipate where these orange dots could emerge in advance, right? You only encounter them when they appear. But in the training time, you know, all we have are the green and blue dots. So in other words, we sort of lack the supervision from unknowns during the training time. And that's being one of the major challenges. And in the high dimensional space, there can be an enormously large, space for these unknowns to emerge, right, outside our in distribution data. So that also causes difficulty in terms of anticipating uncertainty in that high dimensional space. And this problem is further exacerbated by the high capacity neural networks we're working with nowadays. And the good thing about, modern neural networks is that it has this surprising fitting power and expressivity in terms of, performing or fitting really well on a given data set or task. But the curse of using these powerful, function approximator is they can actually produce ill-fated decision boundary, which is not well suited for OOD detection purposes. And so to explain what I mean, I would like to just, use a very simple toy example. I like the toy example. I like simple examples because it really helps getting the point across in a easily understanding manner. And so what we're looking at here is an distribution that's composed of 3 Gaussian distributions, right? So we have class 1, 2, 3. Each of them is drawn from a Gaussian distribution. In this case, it's from 2D, right? Very, very simple setup. And it turns out you can take a very simple neural network. It doesn't have to be convolutional. It doesn't have to be half fancy as like transformers. You can just take multi-layer perceptron and perform this empirical risk minimization to minimize our classification error. And if you do so, with a 2-layer or 3-layer MLP, you can reach pretty decent, almost perfect classification accuracy. And so the resulting decision boundary looks like this, right? And so basically, this learned classification decision boundary looks like this triangular shape, right? So you see this, basically this curvature that's kind of on the top. Anything that's above the curvature on the top will be classified as class 3. And similarly, anything on the relatively bottom left side is going to be classified as class 1, right? So it's a really triangular shape that's carving the space into 3 parts. So with this kind of decision boundary, if we're looking at accuracy measurement on samples that's drawn from our in-distribution, you can almost get pretty good, almost perfect classification accuracy. But what's wrong here is if you look at the OOD detection, it's actually very problematic. For example, those red regions, right? Those red regions highlighting data points that are far away. You can imagine the canvas stretch infinitely. And any points that's really kind of far above, far north, are going to be, confidently predicted as class 3. But in reality, they have nothing to do with class 3, right? And so that's what I mean by, the decision boundary is good for ID classification, but it's, insufficient for OOD detection purposes. And some of you, if you're familiar with generative models, you might be also wondering, well, can we estimate density P of X directly? So, the the difference here in terms of generative modeling versus discriminative learning is that it actually doesn't provide you with the classification ability, right? Which is, this posterior probability P of Y given X. And so that's kind of the setting we're interested in, right? So based upon a model that's performing classification, which by default is not optimized to perform density estimation, how do you actually get some, ID/OOD detection ability out of it? So that's really the dilemma here and the challenge here. And lastly, real world images are composed of numerous objects and components. And so obviously we need to move beyond this image level OOD detection to have finer grained understanding of OOD uncertainty at this object level. So over the years, we have seen this surge of interest in this challenging problem domain. And it's really wonderful to see this thriving literature on OOD detection. And so here's one survey, which I really recommend. My colleagues and I have spent some time composing this a while back, and with the hope that it can kind of help researchers who are interested in get into the space to have a more kind of comprehensive understanding about different methodologies and so on. Of course, I'm not going to touch upon each of those, but I'll try to unpack some of the important ones in this talk. So first, let me, hopefully at this point the challenge has been explained. You're ready to dive into some of the solutions. How do we deal with this problem, right? What are the algorithmic solutions? Is there any hope? So let's take a look together. Here's a method overview. We would typically take a model that's trained on our in-distribution data, say Cypher 10, using empirical risk minimization, right? So the model is only exposed to the in-distribution data to minimize the average classification loss. And once the model is trained, let's take the network as it is without modifying its parameters. And so during inference time for any given input, we're going to devise a scoring function S. And so this scoring function is essentially, the key in a lot of this OOD detection algorithms. And so essentially we're performing a level set estimation here based on this function. We're partitioning all the points in the space into two sets, right? The ones that are above the threshold, the ones that are below the threshold. And if it's below the threshold, we're going to reject this input as OOD, and vice versa. If it's above the threshold, we can produce the class prediction as usual. And so this kind of setup is nice in practice because, in contrast to just having the classifier alone, this additional OOD detector sort of, provides this safety layer, right? To better safeguard this classifier. And so that in case anything, in case it encounters anything off, it can have this ability to catch it. I also want to mention that this problem is slightly different from anomaly detection, which is also a very classic problem that has been around in machine learning for a while. In anomaly detection, it often treats all the data as one class, right, without necessarily differentiating the class labels. Whereas here, our goals are twofold. We're interested in performing classification, which is a multi-class classification task. And simultaneously, we want to learn this binary predictor, which is the OOD detector. All right, so for evaluation, just to give you some context, a common metric is to evaluate the performance of OOD detection using FPR 95, which essentially is saying let's look at the score distribution on the ID data and then pick the threshold so that 95% of the ID data is above this threshold, right? And then we're going to use this threshold to see, okay, among all the OOD data, what's the fraction of OOD that's misclassified as ID? So we want this FPR to be lower than possible, right? In other words, this two distribution, the purple and green, should be as separable as possible. So the key question is, how do we define OOD scoring function, right? I haven't really explained this part yet, and so let's dive in the next part of the talk. So this question has really driven a very rich line of works over the recent years, including ours. In fact, it's really difficult to fit all of them in one slide. And so a common baseline is to use the softmax confidence score, which is defined to be the largest posterior probability, right? So the definition is given here, which is quite clear. This sometimes is also called MSP or just confidence score, right? You're just looking at the output from the softmax layer and then pick the maximum one. However, if we zoom into this highlighted area in this red circle, we notice that this maximum softmax probability can actually be non-distinguishable between ID and OOD data. So here we're taking actually this distribution is based upon a real neural network trained on Cypher10, which is our ID in purple. Then we evaluated against SVHN, which is street view housing number. So these are the setups which I have shown you some pictures earlier in this talk. And so you see that this highly overlapping region, right, actually makes the makes it hard to draw a threshold somewhere to separate out this gray from the purple. And again, this phenomenon is related to the fact that neural networks tend to produce overconfident predictions for OOD data, right? So it's perhaps it's not that surprising. This method is not going to work that well. And later in my talk, I'll explain more why softmax is suboptimal for OOD detection. And so fast forward in 2020, we put forward this energy-based out-of-distribution detection framework, which I would say has the core idea that really influenced many of our recent work. And so I would say a lot of our recent work actually also built upon this this core framework. And so that's why I want to just spend some time briefly introducing how this energy-based OOD detection really works. At a high level, we still have this similar setup, right? We have this input X that's going through this neural network trained on ID data. It's parameterized by theta, which is learned through this ERM. And then we're going to derive this energy score using the so-called energy function. I'll talk about the definition next. And then after this, energy calculation, then we can do this, our usual business. You can plot out this energy distribution and then do this similar kind of thresholding mechanism, right? And so here we flip the sign of energy just to align with the convention. So here the x-axis is plotting the negative energy. And so usually energy is actually smaller for in-distribution. And so once we flip the sign, you see the in-distribution is having, resides relatively on the right side. And so energy model was first introduced to machine learning in the 80s, and it has been around for a long time, decades, in fact. And to give you some background, an energy function takes an input x, let's say my cat, and then the corresponding label y. And so this energy function E of x comma y would take the photo and the label to produce a measure. And this measure is a scalar, right? So think of this measure as some compatibility between x and y. And it should give a lower value if these two are highly compatible. So in this case, the cat photo and the cat label is indeed compatible, so the energy would be low. And the function can be non-probabilistic, and you can turn this into a probability density using the Gibbs distribution, right? So then you can write out this posterior probability in this form. And so again, this is the same equation I showed in the previous slide. And the denominator, which is also known as the partition function, essentially takes the integral over all the possible y state, right? Imagine it's all the possible labels. And then by equalizing these two sides, we can derive this energy. This free energy can be expressed in terms of this negative log of the partition function. And so this notion has been around. It actually, it was originally in physics for a long time. And so far, nothing is new here. I'm just, telling you stuff that's been around for a long time. And so how is this energy-based model related to neural networks and out of distribution, right? So that's something I want to bring in here. And it turns out a neural classifier can be interpreted from an energy-based perspective, right? So let's think about this neural network, which is producing this logit F1. These are the pre-softmax output, right? F1, F2, and so on. And then we typically pass this logit through the softmax that would normalize all this output into some meaningful probabilistic vector that sums up to 1, right? And so that's what we're essentially using. This is the common softmax formulation, which I'm sure, a lot of you are familiar with. And so now if we define these energy function E of x comma y to be the negative of the logit or that corresponding label, effectively this turns into something, right? That's we just saw earlier. This is the Gibbs distribution that's used to normalize the energy values. All right, so recall this is how free energy was defined earlier. Now in the context of a neural network, the free energy essentially replaces this integral with summations through across k discrete classes. And so now for every input x in some neural network function, right, we can compute this very easily using the negative of this log sum exponential operation, right? So this is the definition of energy. And so with energy scores, now coming back to this issue of OOD detection, it turns out these distributions between ID and OOD becomes much more separable. And as I mentioned here, to align with convention, yeah, we're just flipping the energy. Just to keep in mind that in distribution is having actually lower energy and vice versa. So now if we put these two together, right, there are two kind of scoring functions we have talked about. One is the softmax one, and the other one is energy score. And so if we look at, how softmax is defined, it's really a posterior probability, right? P of y conditioned on x. That's what's highlighted in the first line here. And energy, on the other hand, is really the negative of this log of the softmax denominator, right? And so interestingly, if we rewrite this posterior probability to be the joint probability P of x, y divided by this P of of x, which is the likelihood, you see that energy function has some inherent connection to the log likelihood, but it's not exactly identical at this point yet, which we'll come back to this point. But I just want to kind of contrast how you should be thinking about softmax versus energy score. So in fact, energy score is closer to the, ultimately we want to use something that's equivalent to, P of X, but that's very expensive and intractable to estimate. But the definition of energy is kind of one step closer to that compared to softmax. I won't go into the details here, I think, for the time being. But in the paper, we show that minimizing the cross entropy loss, which is this loss formulation here, essentially pushes down the energy score for the ID data during the course of training. And so this can be proved by analyzing the gradient of the loss in terms of how they change the energy states during the training. And so now if we look at the softmax score, or precisely the log of the softmax, it can be decomposed into two terms, where the first term is energy, which we know that it's going to be lower for in-distribution data. And the second term is the maximum logit, which is going to be higher, right, for the in-distribution data. And you see that it's actually, having this opposing force between these two terms. And so the overall summation actually results in a very biased estimation that's not suitable for OOD detection. And to evaluate and compare our approach with softmax confidence score, we train a model Cypher10 and then evaluate against SVHN. And so here, the way we're measuring this performance is using FPR 95. Right, just to remind you, it's basically the fraction of OOD data. It's a fraction of SVHN that's misclassified as ID when the threshold is chosen based on this 95 percentile. And so here the FPR using softmax score is around 48%, whereas using energy score can bring this down to 35%. And so we're already observing quite significant improvement here. And so this slide intends to show that across a broad collection of test data set, we observe consistent improvement here. And again, this approach is also pretty easy to use and doesn't require any hyperparameter tuning. And so definitely more advantages. So far, I have, told you quite a bit about scoring function. But these are only part of the solution to how we, ultimately should build a perfect OOD detector. And in my opinion, these are insufficient if we want to fundamentally mitigate the problem. And so in my view, this mitigating the OOD risk actually requires us to rethink how we design machine learning algorithms from the get-go, not just from, the test time perspective as a patching or as a, add-on. We really have to think from the root of how the moment we're training these neural networks. So to explain what I mean, let's revisit this example. This model is trained on, using ERM on the in-distribution data, right? We have 3 classes, 1, 2, 3, and then ERM is just minimizing the classification loss here. And so recall that the decision boundary is, is giving pretty good classification accuracy, but it's, it's not reliable for OOD detection purposes. And so the reason is that these existing learning algorithms are primarily driven by optimizing accuracy on the ID data, but they don't account for these uncertainty, right, from outside ID data. And so going beyond this standard cross entropy loss, we need to think about this training time regularization that allows us to explicitly account for uncertainty outside the ID data. And so the ideal decision boundary should be something like the right-hand side, which is more in line with our data density, right? That's kind of nicely surrounding our in-distribution data. So how do we go from left to the right hand? To do so, we advocate for this do objectives in learning, which is a combination of standard cross entropy loss, which minimizes the risk on the in-distribution data. So that's part we already know pretty well how to handle. But in addition, the interesting part is the right-hand side, right? We have this additional uncertainty regularization term that's trying to separate ID versus OOD data. And so now let's zoom into this regularization term here. So how should we formulate this risk term? Now let's assume we have access to some auxiliary outlier data. For now, I'll come back to relax this assumption later. So suppose you have some, provided with this auxiliary outlier training data, and then the idea is to explicitly push the energy score to be apart between the ID versus OOD data, thresholded at maybe 0. So basically, for all the ID samples, we want to make sure the energy score is below 0, or for negative energy score, you want it to be above 0. And then for OOD, we want the energy score to be above 0, right? And so this objective has some nice mathematical interpretation too. Essentially, we're performing a level set estimation based on this measurement called energy. And recall, this energy is related to this log of px, but it's not, exactly identical, because you can always multiply the denominator and numerator without changing this posterior probability. But the nice thing is, here we don't have to explicitly optimize for perform this density estimation. So the point I want to make here is it actually suffices to solve a simpler problem that's separating this entire space into 2 sets based on this measurement of energy without having to, estimate P of X exactly for every single data point. So that's actually a harder problem that might not be necessary for OOD detection purposes, because all we need is being able to separate our space into 2 parts, ID versus OOD. And it's okay if some of those data points is not having exact P of X. And so the result of this training is more separable distributions measured by energy score on the right-hand side. And so you can see in this plot here, the FPR can be further reduced down to 1%. And this is as a result of modifying this learning process. And so this looks quite promising, but it does have a caveat because it requires us to have some auxiliary outlier data for training. And so that's that can be, in practice, difficult to obtain. So if you have read this outlier exposure paper, one assumption that's commonly made there is, okay, this auxiliary outlier data is something that's kind of already separable from ID data. But in practice, how can you achieve that easily, right? You have to really go through a careful cleaning process to curate that data set to ensure this nice property of auxiliary outlier data set, which creates some inflexibility and constraints in reality. And so the question really is, where do we even collect those data from? And how can we, get rid of this assumption, right? Is there any way we can generate outlier or OOD data automatically for free that we can utilize to regularize our classifier? So this motivates our study, which was in collaboration with my PhD student, and this was led by Shifeng Du. And so this project is called Virtual Outlier Synthesis. The key idea here is to synthesize outliers in the feature space, which often has much lower dimensionality than the pixel space, right? Because when it comes to synthesize, a lot of people have this association with, maybe GAN-based generative models. But those can be, sometimes intractable to work with because they operate in much higher dimensionality. Whereas our key observation here is, actually for regularizing neural networks, it suffices, at least it allows us to regularize this decision boundary if we just have this feature space outliers. And so here's how it works. We would first model this feature representations. In this case, the penultimate layer of this neural network. In this case, we're going to model this as a class conditional Gaussian distribution. And so the mean and covariance can be estimated on the samples, ID samples empirically. And once we have this empirical estimation, we can then sample, right? We can then sample from these distributions per each class. And so the way we're sampling is to kind of retain those low likelihood points, or in other words, these dark brown points that have likelihood smaller than some epsilon based on this estimated distribution. And you can do this for each of the class in the ID data. For example, now we have 3 different ID classes in the embedding space. And for each of them, we can estimate this class conditional Gaussian distribution and then do the sampling. And all these dark points are the synthesized outliers that we're going to regularize our neural networks. And so once these dark points are generated, now the interesting step, right, is how we're going to leverage them to regularize our classifier. And so we basically take these synthesized virtual outliers. Remember, they actually live in this H space, right? They live in this feature space that's of the same dimensionality as the penultimate layer. And then we can take these synthesized virtual outliers and pass them through the fully connected layer. And you can do this through this linear transformation by multiplying with this linear weights, right? W classification transpose with this V. And then you can obtain this output F of V for the sampled virtual outlier. And once you have this output, these are the pre-softmax logit, right? We can then calculate this energy scores by plugging in our definition of energy. And that's relying on all the output for a given sample. And so now putting everything together, basically we have this joint optimization that's catered to both. Not only we're taking in-distribution classification into consideration, but we also, encourage this network to produce more conservative decision boundary by having this the second term. And so the second term is pushing the virtual outliers and in-distribution to have, different energy scores. And VOS is a general learning framework that you can use for not just classification, but also object detection as well. So in case of object detection, all you need to do is to add this additional term for localization. So now we have classification, a localization head, And then the third term is the uncertainty regularization is the same as before. And so here's some core results. So this is based on object detection network without BOS, right? You saw this helicopter is misclassified as truck, whereas on the right-hand side, if we actually change how the network is trained from the training time, right? Reformulate this training objective, this helicopter can be, better handled as unknowns. And here in this example, we take a model that's also trained on the BDD dataset and then evaluate against this particular sample, right? The stormtrooper is successfully detected as OOD. Admittedly, one of the limitation in our original BOS framework is this distributional assumption, right, that we have to make on the feature embedding. And it turns out you don't actually have to make any assumption on the feature embedding. And this was done in our follow-up work, which appeared at iClear this year, called the non-parametric outlier census. And this is joint work with Lei Tian, Shifeng, and my colleague, Jerry. And so this framework allows us to sample virtual outliers without making any distribution assumption about the feature embedding. And so you can work with any kind of arbitrary geometry of the features learned. And so it has stronger generality and flexibility. Feel free to check this out if you're interested. And beyond the synthesizing outliers, we also attempted to ask this question of how do we obtain, natural outlier training data for free? And so the answer to this question is also yes. So I think in terms of future research opportunities, there is this opportunity in terms of leveraging what we call wild unlabeled data for OOD detection. So what do I mean by wild data? Let's say you have trained a self-driving car to classify car, trucks, and pedestrian and bicycle. And once you deploy this model in the wild, right, basically the model is going to naturally receive a lot of samples for free. It's basically all the data that the model will encounter once it's been deployed. And among those data, some of those are in distribution, some of those are out of distribution, and it's a completely heterogeneous data distribution and completely unlabeled. But the nice thing here is the data is available in a great abundance, and it's often, it captures the true test time distribution, right? Because, some of those samples will be OOD, the true test time OOD. And so mathematically, we can formulate this P wild to be a mixture distribution of P in and P out under some mixing ratio. And so the question is, how can we leverage such wild unlabeled data to benefit OOD detection, right? And so we have made some initial progress. I won't go into the details here, but if you're interested, definitely check out this works. Cool. I think I'm reaching the end of my allocated time here. Just to recap and summarize this talk, I think a key message I do want to share with the community, with the audience here, is we really need to think beyond, the standard cross-entropy loss when it comes to training our neural networks, because they're insufficient, right? They're kind of ill-fated for the OOD detection purposes. And so by reformulating how we train these neural networks, we can provide much stronger safety performance against OOD detection. And so this requires us to explicitly account for these uncertainty OOD during the training time. And I've introduced a couple works along this line, that has hopefully shed some light in terms of how we approach this problem. Yeah, in the end, I just want to share this figure, one of my favorite figures again, right? The left-hand side is what's produced using the standard cross entropy, and on the right-hand side is, I think, where the opportunity is how do we design more conservative, right? Design learning algorithm that promotes this conservative decision boundary that's more in line with our in distribution data. And I think there's a lot of open questions and opportunities out there. With that, I would like to thank you everyone for being here. And if you have any questions, I'd be glad to take those.
Okay, cool. Thanks, Sharon, for very detailed explanations and wonderful insights here. So I'm just wondering whether anyone has questions. Please feel free to ask. Yep, Anton.
Yeah, hi Sharon. Thanks so much for that. It was really interesting. I'm just wondering about how this applies to non photographed systems. So, for example, I'm more in the clinical area, and we get patient data that comes through that's not digital imaging, but just standard tabulated data. And the way that you seem to do your out of distribution within distribution was around classification. So if we've got a binary classification to predict whether someone's got sepsis or not, then there's just the two cases. So I was trying to work out how you could use your technology and apply it in our scenario. But what does out of distribution mean? Because the patients either have sepsis or they don't have sepsis, and there is no third case, if you know what I mean.
Thank you for that question. I think that's definitely, one thing that comes up a lot, when we bring up this OOD detection problem. I think in this most classic setting, or in the most natural setting, working with image-based data is often, like a very natural starting point. That's indeed where, a lot of this OOD detection literature has taken place. And recently, we're also kind of, looking into going beyond this image-based detection to look at other modalities, including text, for example. And I think what you brought up in terms of tabular data in this clinical setting is also definitely one interesting one, though we haven't we haven't kind of looked into the tabular data. So I think in order to provide a kind of more better insight in terms of how to, what's the kind of most suitable OOD detection mechanism, or how do we even define what we mean by OOD there, in practice, it can be application dependent, right? And I think this may actually requires maybe a further conversation. I would be happy to kind of understand better on this problem setup, on what are the clinical, let's say the record is trying to classify, and depending on the use cases, perhaps OOD needs to be tailored and defined accordingly.
All right. Thank you very much. It was a great talk.
Thank you so much for the great question.
Cool.
Yeah, hi. Once again, thanks for the talk. It was very intuitive. So I just have a question about the assumptions you are making. So I remember that in the problem formulation, you're assuming that all the output, all the OOD samples are not part of the labels, but I would imagine in real life scenarios, the out of distribution data could be one of the labels that you're predicting. So I'm just wondering if you're focusing on OOD detections, wouldn't that limit the extrapolation properties of your neural network? Or is that something that you can control through the OOD detection?
Yeah, thank you for the excellent question. I love that. Actually, one thing although I kind of mostly focus on the semantic shift aspect of OOD in literature, there are, I would say, two primary types of OOD, right? I think what you're hinting upon is this covariant shifted OOD, where the samples, despite being sampled from maybe a different domain under this different P of X condition on this Y, but nonetheless, Y still belongs to one of this existing training categories. And so in this case, we design this OOD generalization capability, right, to be able to predict them correctly into one of the training categories despite the shift. So it turns out that I think in the literature, there's often kind of two schools of effort pursuing these two problems relatively independently. But recently, we do have this, I personally think it's a very interesting paper. For the time being, I couldn't, I didn't have the time to put together slides to share this. But it's our latest ICML paper called Feed Two Birds with One Skull, leveraging wild data for both out of distribution generalization and out of distribution detection. And so the motivation of that paper is really try to come up with a unified algorithmic solution, right, that not only caters to this semantic OOD that could occur in the wild, but also being able to generalize, right, to this covariant shifted OOD data. If they were come from the same training categories. So I would highly recommend maybe checking out that. And I think, in general, that's definitely, I think, a direction that these two communities should think more about, is how do we tackle these broader distribution shift problems together.
Yeah, thank you for the answer.
Yep.
Okay, so we have two more questions posted on chat.
Oh, sure. Let me see if I can access my chat here. Or if the audience or whoever posted the question is still on the call.
Yep.
You're more than welcome to unmute yourself and ask.
Rihong, are you here?
Yeah, hi. Thank you for the great talk. I have a question about the results. I saw the results of the helicopter image, and I don't remember the page number. I can see that the OOD detection seems like it will decrease the confidence of the correct classes and the bounding box detections. Is this a problem?
Oh, thank you for that. I think that might happen due to, in this optimization, because these were two kind of independent runs, right? One that's based upon a different kind of training trajectory. So it's possible that you're seeing this slight kind of difference in terms of confidence for the in-distribution class. But what we measure actually in the paper is for those, let's say, test samples coming from the let's say Berkeley deep drive or whatever, the in-distribution data set, the MAP remains largely the same as the baseline when we're not, adding this regularization. So in other words, these random variation could exist, from when you look at some of the visualizations due to different runs and randomness in training. But I think a more reliable way is to actually look at, on average, whether the MAP changes or not after adding this. And we show that it's actually possible to retain this MAP while improving this OOD detection ability.
Thank you.
I just have a follow-up question regarding Rayhon's the question about the Wallace paper. So because like we are currently doing object detection problems. So once we generate some bounding boxes proposals, and then we crop the embeddings from the feature map, then what we want to do is do like OOD detection, right? So if we use some kind of metrics like energy score or whatever to do the thresholding and want to separate them out from the scene classes and the OOD ones, but it could potentially be the background. So just wondering if in the Vols paper, have you compared like whether it's valid to use the same thresholding method to separate out the background and or the objects?
Let me think back. I think there is I think it really depends on the architecture in terms of the object detection model that that you're using. And you know, in practice, there's often a separate kind of, you know, background detector and a threshold, right? That has to be kind of chosen properly in order to make sure that that the bounding boxes that are being highlighted, right? The proposal networks is indeed highlighting with large probability a valid foreground object. And so that's actually one thing to double check and be careful about. Otherwise, you know, if we're not careful, potentially there could be many proposals, right, that are flagging these background, and that's not what we're interested in. So we're interested in assuming among all the boxes that are being kind of being highlighted or by this proposal network, and assuming they're all foreground, what's this classification, what's this detection error in terms of classifying them into ID, one of the in-distribution categories, or OOD. So that's kind of the primary metric we were looking at. But definitely, I think ruling out this background is an important issue when it comes to evaluation.
Yeah, cool. Thanks for answering. So
Yep.
one more question from sorry, two more questions. One from Jason.
Hello.
Yep.
Hey Sharon. Thanks for the wonderful talk, by the way. So recently I was reading this paper called ASH, Extremely Simple Activation Shaping for OOD Detection. I don't know if you've encountered this this paper. It's published at iClear 2023 as well. But anyways, it basically discusses like removing a large portion of activation, and it seems like it will improve out of distribution detection performance. So I guess in line with that, have you encountered any other efficient adaptations or some sort of pruning techniques that would improve OOD detection? And also another thing would be, do you see this exploration as a promising direction for improving OOD detection?
Yeah, thank you for that. That's a very interesting question. So, you know, interestingly, the work that you brought up is actually inspired by two prior works from my group, and that happens to be,
Right.
you know, DICE happens to be. It's actually the first paper that I wrote with my students here in UW-Madison, and then React is kind of a work that EO did in the following semester. And so that kind of, I think it has this, I would say, at that time, I think it has this interesting kind of perspective, right? Looking at, okay, really trying to understand what is causing, like if you look at this React paper, one of my favorite insights in that paper is to be able to explain by examining these internal activations, to what extent are the OOD activations differ from the in-distribution data, and why is this, you know, in that paper we observed this kind of epsilon scale distribution, which is largely chaotic and more abnormal for the OOD data compared to the ID data. And so one of the insight there is really what is causing this large or abnormal activation is the fact that we're using batch normalization just wrong, right? We're taking batch norm statistics that are estimated on ID data, but blindly applied for the OOD data. And so I think that was a pretty cool insight that I really liked about. This is definitely, an interesting direction to think about, how we can, by either pruning out or kind of attenuating some of the activations to better aid the separation between ID and OOD. And so I would still view this as post-hoc OOD detection, which means these are the techniques that are operating on a model that's trained with, let's say, cross entropy loss. But my opinion is still that these are methods, if you're stuck with this post-hoc setting, that you can't really kind of change your neural network that's already being deployed in practice. But if you can, it's actually much more effective to fix this problem from the get-go, right? To fix this root problem, we really need to kind of rethink how we design these learning algorithms during training time that can already facilitate this compact decision boundary, or maybe, mitigate this chaotic activation that we're observing in this post-hoc time. That to me is perhaps is a promising direction that's worth looking into and investigating.
Yeah, great. Thanks for answering.
Yeah, thank you for all the excellent questions.
Maybe one last question from Jomo.
Hi, how's it going? I just had one kind of question, and it was kind of a follow-up to Jason and Yadan's questions. So I feel I've seen some like visualizations of some of the detections from these models, these OOD models, and sometimes what it gets confused on, or what it seems it gets confused on, is kind of the background is like you might have two data sets, and the background might be pretty similar between the two data sets. So like in these data sets, like ImageNet and that. They're actually very well framed. Like you have an object in the center of view or something like that. And that's the same between like SVHN and all that kind of thing. So what do you think is the main contributor to like the kind of error rate in OOD detection? Like what lies near the threshold of your determining of OOD?
So you're asking if we're looking at the errors.
Yeah.
So maybe we can go back to this. Actually, there is one.
Yeah,
Maybe
like where it overlaps between OOD and ID.
Exactly. So you're asking, okay, what are the characteristics of the samples that are more overlapping with this with the ID part, right? From the visual perspective.
Yeah. So is it like a semantic problem, or is it like the model gets confused about something else, or is it that the data, like the image, looks pretty similar despite there being a different class there?
I would say, it really depends on, I think, the in-distribution and OOD pairs we're looking at here. And the problem that you brought up can definitely happen, which is when the OOD data shares some kind of similar features, such as the background or even some other features, right? In some other cases, the semantic features might also be very close. Like if you have trained like a cat versus dog classifier and you're evaluating against like a fox, right? The fox can trigger some of those neurons because of the shared features there. So the issue can be kind of, I would say, multifaceted. In this particular example we're drawing here, this is based upon a neural network that's trained on Cypher10 and evaluated against SVHN. And so it's possible, if we look at these samples here, right? So it's possible that some of these SVHN samples that may have this light, blue, whitish background, and that may share, with respect to this airplane. Some of those airplane pictures are also having this kind of, very light blue sky-ish background. So that's one possibility, right? I think it's definitely one scenario that could trigger these the similar features. And the feature, once you pass this through the linear layer to the final output, all this could manifest as large output and high confidence prediction.
Okay, thank you.
Yeah, but I think, one thing I think, frankly, we actually haven't done this, very fine-grained error analysis, and as far as what you're posing here, I think it will be very interesting to actually, this requires, I think, from the human inspection side to really do this kind of qualitative analysis on the errors, which is actually not often conducted or done in the literature. So I think that could be very insightful and valuable.
Yeah, definitely. It's hard to understand what's going wrong when you just look at like some metrics like FBR 95 or something like that. Yeah.
Exactly. Sometimes these analysis might actually inspire, this may review some of the intricate phenomena that we're not aware before, and may in return inspire some algorithms, new algorithms. So that could be interesting too.
Yeah, thank you.
Yeah, thank you.
Okay, cool. So probably should end up here due to the time limit. And thanks again for sharing to taking the time to for every like Q&A and the insights sharing. And thanks again for attend our sessions. Okay.
It was my pleasure. Thank you, everyone.
Thanks. See you guys next week. Bye.
Bye, everyone. Have a good one.